previous part, we discussed the basics of linear programming. Why do we use them? What are linear function? What is a maximization objective function? What is a minimization objective function? What are decision variables? What are objective coefficient? What are constraints, their purpose, and their kinds? And lastly, we talked about 4 rules about linearity, the continuous variable assumption, the certainty assumption, and a non-negativity assumption. Now, linear programming is just a concept, and there are further methodologies in linear programming. So if we have a linear programming model, then what are the methods through which we can solve a given linear programming model? That depends basically on the decision variable. Now, what are decision variables? You can watch the part first of this brief lecture summary video, and you will get those. But once again, decision variables are simply the proxies of real products in a business, or some entities which we take just as a representation, right? Now, if the decision variables are 2, we can, what we call, use the graphical linear programming, the building block of the methodology concerning the linear programming. But if the decision variables are more than 2, right, then we tend to an interesting method, which is actually called a simplex method, that is much more advanced compared to the graphical linear programming. Graphical linear programming basically consists of all the basic concepts that will be later used in the rest of the methodology. So at this stage, I'll only talk about these 2 methodology, one the basic one, and the other one is a little more advanced in nature. So first of all, graphical linear programming. Now, what is a graphical linear programming? As I discussed in your part first, that there is an objective function, and then we have some constraints, right? So for instance, if I write something like this, we have an objective function, maximization objective function, a mathematical function, which is z equals 5x plus 3y. Now, what is a x? What is a y? These both are decision variables. Now, we want to actually maximize this linear function. Why the linear function? Because the exponent is 1 and 1. We have basically 2 constraints. Just for example, just for the purpose of understanding, I'm just taking 2 constraints right here. And by the way, as I discussed earlier, we have only 2 decision variables, so we can use graphical linear programming. If there was a 3rd decision variable, then we cannot use the graphical linear programming. Graphical linear programming only works in 2 decision variables. Now, the constraint is of less than or equal to sort. So for instance, if I write something like this, 3x plus 5y, that is less than or equal to 15, and 5x plus 2y is smaller than or equal to 10. So as we discussed in our part number first of that summary video, these 2 values are what we call the right-hand side, and these are the left-hand side. So the value consumed right here should be either equal to or less than this value right here. That's why we call it a constraint. And these 2 constraints basically limits the value of the maximized objective function. Now, how to proceed? How to proceed with the graphical linear programming? First of all, what we need to do is we need to plot these inequality on a graph, right? And there are several methods to graph the inequalities on graph. So first of all, the graph, right? So that's a basic 2D graph consisting of a value of x. That's the origin. So if we move away from the origin towards the x1, we get the positive value. So these are the positive value. If we move away from the origin towards this y, we get the positive value of y. Now, if we move away from origin towards this side, we get negative value of x, which we called x prime, and similar for the y prime. So if we move away from origin towards downward, then we get negative values of y. So if I write something like this, x is greater than 0 and y is greater than 0 for any point placed in this first quadrant. We call this a first quadrant, this one is the second, this one is the third, and lastly, this one is the fourth. So if I place any dot anywhere, these both will have positive values, which is basically greater than 0. So both the values are positive. But if I place any dot in this quadrant, in second quadrant, so this will mean that the y will have a positive value. So y value should be greater than 0, but the x value should be a negative value. So x should be smaller than 0, a negative value. So here we have a negative value of x, but positive value of y. In third quadrant, both the values are negative. So if we trace it to its origin, here the value of y is negative down below, and the value of x is also negative. And what we can call it, x is smaller than 0, and y is also smaller than 0. So both the values are negative and negative. In the fourth quadrant, if we place any dot anywhere, so it would basically correspond to 2 values. That is positive value of x, but negative value of y. So here the positive value of x, but negative value of y. So why am I saying that? Always remember that the solution of a linear programming problem using graphical linear programming will always lie in the first quadrant. And why is that? So in the first quadrant, if we represent a decision variable, one with x and another one with y, just 2 decision variable on which we can apply graphical linear programming. So according to rule number 4 of non-negativity, the value of decision variable needs to be always greater than or equal to 0. So which is the only quadrant that accommodates the positive value of both the x and y? That is only the quadrant first. So the rest of the quadrant we cannot use in linear programming, or the solution will only lie in the first quadrant. So now, once we are done with the graph introduction, very basic introduction to graph, where the solution will lie. Now, what we need to do is we need to plot these two constraints with a method on this first quadrant, right? We need to plot them right here. How to do that? There are several methods. So one of the method is what we call, if I see what's a line, so it's simply the space between 2 points, right? So if I want to plot a line on a graph, I need 2 points. And that's what basically we need to do. We need to actually construct 2 points out of inequality number 1, that is constraint number 1, and 2 points out of inequality number 2, constraint number 2. So once we get 2 points from this one and 2 points from this one, what we will get is a line. Now, how is that? Quickly. So what I will do is I'll just make a very simple graph right here. And that's the origin. And the origin, the values are basically 0 and 0. And this is x, this is y, and this is x prime, and this is y prime. So we'll not use this quadrant, or this quadrant. I'll just zoom it a little bit. And now let's form our scale. So let's suppose it's a 1, and let me make it a little bigger. So let's suppose that's a 1, that's a 2, that's a 3, 4, and 5, and 6. And here we have 1, 2, 3, 4, 5, and suppose 6, right? So x is of x and x is of y. Now, moving on. What should I do? I'll just take the first constraint, and then you can extend this method to the second constraint as well. So I'll write this constraint right here, 3x plus 5y is smaller than or equal to 15. I need to construct 2 points. For that, I will do a mathematical trick. First of all, I'll just shift this inequality into equality. So the equation will become something like this. It does not change anything mathematically as long as I don't shift any of the constants or any of the variables around. Right now, I'll split this equation into 2. 3x plus 5y equal to 15, just the replica of it, right? And 3x plus 5y equal to 15. Now, I'll do a mathematical trick in which initially I'll take this x0 in this equation, and then I'll take y0 in this equation, and I'll get 2 points. How is that? So if I take the value of x0, and on the other side of equality, I have 15, what should I multiply with this 5 so that the equality is satisfied? So the answer is really simple. I can simply multiply 3 with it, and it will become 15 and 15, right? So equality is satisfied. So now I can write something like this. I'll make a small grid. I'll write x here, y here, and this I'll call point number 1, and this I'll call point number 2, because that's our basic objective, to split this equation into 2 points. Excuse me. So initially, if I take the value of x0, what was the value of y? The value of y was 3. Now, I can plot this point 1 on the graph. How is that? So if the value of x is 0, the value of x is 0 towards the origin, then the value of y is basically 3. So value of y, 1, 2, and 3. Now, we have done our partial work. Now, to the other side. Now, what I will do next is this. Initially, I took the value of x0. Now, I'll take the value of y0, keeping the rest of the things almost the same. Now, what should I multiply with 3 so that the equality is satisfied? So the answer is really simple. I'll simply multiply it with 5. So if I multiply it with 5, this is 0, this is 15. So hence, the equality is satisfied. We are fine here, we are fine here. So now we can write something like this. So when the value of y is 0, the value of x is simply 5. Now, let's plot this point. So I'll plot it like this. So if the value of y is 0 right here, what's the value of x? The value of x is 1, 2, 3, 4, and here you go, it's 5. Now, I can simply do what? I can simply join this yellow dot with the red one, something like this. And here you go. You have basically plotted the inequality 3x plus 5y greater than or equal to 15. That's your constraint number first. You can use the same method on the second equation. And tell you what, you can pause the video, split this equation into 2 points, plot it, and then you can basically check the answer if you're correct or you're incorrect. Now, here you go. I'll show you now the answer of it, right? The representation of it. So it's something like this. That's the second point. So we have an equation 5x plus 2y smaller than or equal to 10. So if I take the value of x0, what should I multiply with the y so that on the other side the equality is satisfied? So it's a 5. Then in next turn, I will take the value of y0. So if I take the value of y0, what should I multiply with this x so that the value becomes 2? The value becomes 10, hence satisfying the equality, that is 2. Now I simply need to plot this point number 1 and point number 2 on the graph, which is basically represented by the green dots. So if the value of x is 0, what's the value of y? The value of y is 1, 2, 3, 4, 5, and the green dot. Then again, if the value of y is 0, so the value of y is 1, 0, what's the value of x? The value of x is actually 2, 1, 2. And we have actually plotted another constraint, which is 5x plus 2y. Now, tell you what we have done, our job of plotting constraints, these two constraints. Now, what else to do? What's the next step? So if we see, and let me zoom it out a little bit, excuse me, in the first quadrant right here, you will see some mathematical shape. And these shape are basically foreign numbers. So mathematical shape 1, geometric shape 1, geometric shape 2, geometric shape 3, and geometric shape 4. Now, one of the steps in a graphical linear programming is to identify a feasible solution space, feasible solution space. And feasible solution space is that geometric shape in which the answer of the maximization of this linear function is hidden. So now we have 4 regions. We have 4 regions for geometric shapes, in which one of these is what we call feasible solution space, which basically represents the combination of the decision variable and the maximize value of z. How is that now? These 4 shapes, which of them is now a feasible solution space? There is a very simple method for that. I'll once again tend towards the constraint, which are basically, what are those? Let me have a look. 3x plus 5y smaller than or equal to 15, and 5x plus 2y smaller than or equal to 10. Let's see if I can remember those. So constraint number 1 is what we call 3x plus 5y, and this is basically 5y. I hope I'm right, 5y less than or equal to 15. That's your constraint number 1. And your constraint number 2 is something like this. It was, yes, it was 5x. This is again 5x plus 2y smaller than or equal to, what was that? 15, I guess it was 10. Let's check it. So 15 and 10, 5x, yes, it's fine. Now, I'll use a simple mathematical trick. What's the trick? The trick is basically what we call the true and false. If, what am I doing after some time? If its answer or if the argument is true, what I will do is I'll shade below this constraint, this yellow constraint towards the origin, right? That's simply a shading game in this graphical linear programming. So if I am doing something with this constraint right here, which I'll tell you in a while, and if in the end the thing is true, the argument is true, I'll shade towards the origin below that yellow line. So what I'll do is this. In the first point, when I was splitting this inequality in 2 points, I supposed equality for that. Now I'll remove equality and I'll write this inequality something like this. So nothing changes again. That's fine. I simply remove the equality sign from it. Now it simply says 3x plus 5y is smaller than 15. Not equal to. It's smaller than 15. Simply that. Now in next step, if I ask you what are the value of x and y at the origin, these are 0 and 0, right? So I'll simply place the value of origin in this inequality, something like this. So if I solve it, it will become 0 is smaller than 15. Now let me ask you, is that mathematical argument correct or incorrect? 0 is smaller than 15. Obviously, it's true. So if it's true, what I need to do is something like this. And I will do it something like this. Now, I'll take this red color. And I did it for this constraint right here. And the argument is true. So below that constraint line, I'll shade something like this, right? I'll start shading like this, all the way towards the origin. So that's the first shading corresponding to constraint number 1. So all the way down below the constraint, all the way towards the origin. That's the first shading. Now for the second equation, same method, right? So I can write it like this. That is one of simple mathematical assumption. I'm just removing the equality. And again, I'm taking the value of origin. So in each of the cases, in order to find the feasible solution space, you will take the value of origin in the decision variable x and y, or any decision variable, right? But they should be 2 in number. So if I write again something like this, so this is 0, 0 is smaller than 10. And is this mathematical argument correct? Yes, it is correct. It is again true. So what will I do? Now I did that for that green constraint, right? The green line. So I'll do something like this. So I'll take this blue color, right? And I'll start shading. And this time I'll change different sort of a shading. I'll do something like this, dots, right? And all the way down below this green line, I'll shade it. I'll shade it something like this. All the way down below the green line towards the origin, I'm shading. something like this. Okay, now why am I doing that? What's the logic of it? So initially I told you that there are four geometric shapes. So a shape 1, a shape 2, and a shape 3, and a shape 4. Now follow those. In geometric shape 1, you have only the first type of shading, but not the second type. So this means this region only obey one of the constraint, but not the other. So we can reject that. In order for a geometric shape to be a feasible solution space, it should obey all the constraints, or in this case, both the constraints. So geometric shape third, this one right here, the triangle, it only obeys one of the constraint, which is that green one, this constraint right here, but it does not obey the first one because it does not possess its shading. What about this one, geometric shape 2, this one right here? You can see that it obeys the red type of shading, the line shading, but does not the blue dot type shading. So it obeys one of the constraint and not the other. But what about this region right here? In this region right here, in this four-shaped geometric structure, we have both the type of shading, the dotted blue and the line red. So this means it obeys both the constraint. So hence, this region right here is our feasible solution space. Now, what to do with that? Now, moving on. This is now our feasible solution space here. The answer is actually hidden. Now, each geometric shape has a corners. So in this case, we have four corners, corner A, corner B, corner C, and corner D. And all the rest of the geometric shapes, they are rejected. They are not the feasible solution space. We have actually shortlisted the first one as a feasible solution space. Why? Because this region obeys all the constraints. And okay, what if the argument is false? Then what will I do? This is important, right? If the argument was supposed to be a false one, then let me get rid of it and let me show you that. Now, suppose if the answer was something like this, 0 is greater than 15. Now it's a false one. And suppose if it's we actually solved it for this yellow line, then I'll shade away from the origin. Then I'll use the upper side of the constraint and I'll shade something like this away from the origin, starting from the upper side of that constraint line and away from the origin. Fine, simply like that. And in the second one, if it was something like this, right? 0 is greater than 10. Again, it's a false one. What would I do? I would shade away from the origin, starting from that constraint line, something like this. Something like this. Now, once again, in that case, what is the feasible solution space? And you can guess that. So if you see, here you have only the blue shading, here you have only the red shading. This would be then your, what we call the feasible solution space. So point 1, point 2, and point 3. So always remember, if the mathematical argument is false, shade away from the origin, starting on the other side of the constraint line. But if the argument is true, shade towards the origin below that constraint line. So I hope it will be clear now. Coming back to this feasible solution space or feasible geometric shape. Now, what to do next with it? So if you just have a look, each point on a graph represent two values. So if I see the first value corresponds to the x and the next one corresponds to the y. So what's the value of x and y here? So it's 0 and 0. So the value of x and y at point C is, these are actually 0 and 0. What about point D? The value of x on point D is basically 2. What is the value of y? The value of y is basically 0. So point D represents the coordinates of 2 for x and 0 for y. What about the B one? So if we trace it down below, the value of x is 1. While what's the value of y? It's somewhere between 1, 2, and 2.5. And lastly, what are the value combination at point A? So basically the value of x is 0, it's from origin, and the value of y is basically 3. Now we have these values. Now one by one, we'll need to put these values in the objective function right here, x and y. How? It's something like this. These are the values at point A, point B, point C, and point D. So initially, that's the objective function, the function which we wanted to increase in light of the two constraints. So what's the value of x and y at point A right here? That is 0 and 3. So we simply placed 0 in the instead of x and 3 instead of that, and we solved it. We got the value of 9. We did the similar for the rest of the 3 points. And as the underlying concept is to maximize the objective function, we'll always go for the highest value obtained through this method, which is basically the point B. So the point B is the point which we call the optimal point, and this optimal point represents the key to maximize this linear function, which is z is equal to 5x plus 3y. And what are the combination of x and y? That is 1 and 2.5. So it simply means, so if that is the equation, z equals to 5x plus 3y, and we need to take decision regarding the values of x and y in order to maximize this z value. So the combination is, we need to take 1x and we need to take 2.5 y value. In that case, we'll only get the maximized value of 12.5. Now, there is something unique about this optimal point. You cannot increase, and I am saying that again, you cannot increase the value of z, which is a maximization function value, beyond 12.5 with these constraints. If you are using these constraints and you are not changing them, you cannot increase the value of z further beyond 12.5. Now, that is the end of the part second of that small summary video, which